Welcome to the Explainer, everyone. Okay, if you're a developer or an engineer, someone currently out there wrangling language models on a daily basis, you're absolutely going to want to pay close attention to what we've got lined up today. We're diving into this genuinely groundbreaking new piece of research. It's arXiv paper 2607.8774 to be exact, and it's honestly poised to completely change how we build AI systems. It introduces this concept called CogniConsole, and it pretty much challenges everything we thought we knew about getting these massive models to actually behave.
I really want to speak directly to those of you building in the trenches right now. Because, well, you know the pain, right? You hook up this massive state-of-the-art model, it's incredibly capable, but then you deploy it into production and bam, you still run into context drift, you still see hallucinations, the model just inexplicably violates your hard constraints, especially when you're working in those tricky multi-step settings. And the standard industry response has almost always been, well, just use a bigger model, or hey, let's throw more training data at it. But seriously, why do these highly capable models still fail? This research paper actually isolates a completely different variable, and spoiler alert, it's not the model itself.
Okay, let's dive into this. Here's our agenda. First, the LLM reliability illusion. Second, introducing inference-time control. Third, proof in the probes. Fourth, rewiring developer workflows. And finally, beyond model scaling.
Section 1, the LLM reliability illusion. Scaling isn't the silver bullet.
So, taking a look at this, on the left side, we have the traditional probabilistic approach. This is where reliability is basically treated as this mysterious black box capability issue. We scale up the parameters, we curate these massive data sets, we tighten our alignment pipelines, and essentially, we just cross our fingers and hope for stability. But over on the right is the deterministic approach that this research proposes. Instead of relying on the model to magically self-regulate, it relies on programmatic coordination and bounded reasoning. The massive breakthrough here is really just shifting our mindset. We absolutely have to stop treating unreliability as a lack of model capability and start treating it as an engineering constraint, something we can actually control.
Moving on to Section 2, Introducing Inference-Time Control, the CogniConsole architecture.
Let's break down this term. Inference-time control basically refers to the computational layer that governs task framing and context selection, before text generation even begins. Put simply, it's a formal abstraction that steps in way before the model ever starts predicting that next token. CogniConsole is essentially an architectural instantiation of this exact idea, pulling that crucial control out into a highly structured interface.
And guys, this leads to a massive architectural shift. Think about current agent frameworks or long context pipelines. They generally treat prompts as static configurations. You write a prompt, you send it off, and you kind of just hope it works out. But with CogniConsole, prompts are formalized as actual executable policies. By externalizing this control layer, your system can now enforce constraints, it can manage those massive context windows, and it dictates reasoning procedures, all without needing to touch or scale the underlying transformer architecture at all. It's wild.
All right, Section 3, Proof in the Probes. Let's look at the empirical evidence.
Now, what's really interesting about this slide is that number right there, 489. The researchers didn't just guess that this would work. They rigorously validated their approach through 489 distinct, controllability-oriented probes right inside a multi-step interactive environment. They deliberately kept a fixed base model architecture throughout the entire experiment, literally varying only one single thing, and that was the degree of structural scaffolding.
The results here are just incredibly clear. Looking at this fixed base model setup, as we move from unstructured prompts over to a fully scaffolded density, look at what happens. Output variance drops from high to low. Failure rates systematically drop from high to low. When control is underspecified, the models just suffer from context drift and really inconsistent constraint adherence. But the second that structured interface guides the model into bounded reasoning paths, all of that ambiguity simply vanishes.
So the crucial point is this. Reliability scales with scaffolding density, not parameter counts. Systems that hard-code their reasoning procedures and constraint checks at inference time heavily outperform the ones relying solely on zero-shot or few-shot prompting. The paper basically proves that so many of those failure modes you're seeing in production, they are not capability gaps, they are control gaps.
Okay, Section 4, Rewiring Developer Workflows. Let's get into the developer playbook.
And this brilliantly illustrates the 5 exact workflow changes that you developers out there maintaining RAG pipelines or agentic workflows need to implement today. Number 1, externalize context management. You've got to stop passing raw conversation history directly to the model. Context selection really needs to be a computational operation, not just a prompt parameter. Number 2, replace unstructured prompts with bounded reasoning. Define your task decomposition and your output schemas before the model even generates text. Number 3, treat prompts as executable policies. Actually encode your hard constraints and validate outputs programmatically instead of relying on follow-up prompts. Number 4, measure variance, not just accuracy. You need to track your output stability across identical inputs. If that variance is high, well, you need more scaffolding. And number 5, decouple scaling from reliability. Fix your control layer entirely before you ever even consider scaling up to a larger model.
Which brings us to Section 5, Beyond Model Scaling, Limitations and the Horizon.
Now, it's definitely important to set some realistic expectations regarding the paper's current scope. The validation right now focuses on a fixed model, so it doesn't benchmark cross-model generalization just yet. Plus, real-world deployment latency is totally untested at this stage. And there isn't a public GitHub repository available right now, so you'll want to monitor the arXiv page for any potential code drops. That being said, you absolutely don't need to wait to start building. You can take these control interface patterns they describe and start implementing them directly into your existing orchestration frameworks today, just using standard bounded prompt templates.
This whole paradigm shift is perfectly cemented by one really specific conclusion from the authors, and I'll just read it directly. Reliability ceases to be a black box property and becomes an engineering constraint. The engineering payoff you're desperately looking for in your applications, it's going to come from deterministic control, definitely not from larger model weights. Which leaves us with this final kind of provocative question as we close out this explainer. Looking at your very own engineering roadmap right now, when you push your next major update to production, are you going to be scaling your parameters or are you going to be scaling your control? It's a fundamental shift in architecture for sure, and one that just might end the LLM reliability illusion for good. Thank you so much for joining me, and I genuinely hope this deeply restructures how you approach your very next build.